Hello everyone, I'm Jae Choi. Today I will present our work TMO, Textured Mesh Acquisition of Objects with a mobile device by using differentiable rendering. Thanks to advance in technology, current mobile devices such as iPhone or iPad can produce valid pose tracking results and low resolution depth maps from LiDAR sensor. Our goal is to reconstruct a high-quality textured mesh using all information from mobile device. This is the overview of our pipeline. It consists of three steps: RGBD-aided structure from motion, geometry reconstruction, and texture optimization. We propose the RGBD-aided SFM to refine initial poses from ARKit. To improve the classical geometry reconstruction and texture mapping, we apply a neural geometry representation and neural texture fine-tuning to update 3D geometry and texture maps. Unfortunately, mobile LiDAR has a poor spatial resolution and very noisy depth estimates. Thus, instead of using depth maps from LiDAR, our pipeline builds on classical 3D reconstruction and texture mapping. This is because classical method has many strengths, such as having an explainable pipeline. Therefore, we aim to improve this classical method. Additionally, we refine initial poses from ARKit and obtain highly accurate poses for reconstruction. We first explain RGBD-aided structure from motion. The goal of this step is to refine initial poses from the mobile device. First, we introduce pre-processing method to filter low-resolution depth maps. Second, we propose a depth factor and learn bundle adjustment with this depth factor. This depth factor is a useful constraint for accurate pose estimation and reliable triangulation. Also, this factor guides the scale of the SFM to the metric scale of the depth sensor. This shows the benefits of RGBD-aided SFM. Compared to initial depths with initial poses, our RGBD-aided SFM helps to refine poses for the next step. For geometry reconstruction, we utilize refined camera poses from the previous step. First, we learn the state-of-the-art multiview stereo called ACMP to generate depth and normal maps. In the first stage, we train neural implicit representation for surface reconstruction. We use 3D points and normals from MBS to regularize the geometry network. In the second stage, we don't use regularization laws for training neural implicit representation. After the first stage, we can extract a triangular mesh from the SDF via the Marching Cube algorithm. Then we leverage the popular quadratic mesh simplification to obtain a lightweight mesh. Given the lightweight mesh and multi-view images and camera poses, we utilize classical texture mapping method called TextRecon to generate texture maps. After classical texture mapping, we propose a fine-tuning step by optimizing texture maps. We leverage a differentiable renderer which performs mesh rasterization and then texture sampling to render an image. Then we compare the rendered image with a current view image by computing the photometric loss. Also, we use multi-view photometric loss to fine-tune texture maps. Our smartphone application based on ARKit can capture images, poses, depth maps, confidence maps, and image sensor information. Our method does not need a mask for object. We build two types of dataset, ARKit video and AR capture. We will show the mesh and its reconstructed texture of both datasets. ARKit video collects long video sequences similar to dataset for RGBD SLAM. We use from 50 to 80 images to reconstruct mesh and texture. The AR capture is a multi-view dataset of objects consisting of high-quality 4K images with depth and gravity data. We use less than 50 images to reconstruct mesh and texture maps. These are our comparison results. The left comparison shows the quality of meshes. Both implicit neural surface reconstruction approaches, including our method and Bohr SDF, show comparable performance, and both methods are superior to classical 3D reconstruction such as TSDF fusion and ACMP. On the right part, we can show the difference of texture maps for the mesh. The visual results of our approach are visually sharper and perceptually closer to the ground truth scene. Thank you for watching the video. We will present our work on Thursday, poster and number 19.